For those of you who are interested in how this works and what makes this material so special, the next part is for you. Let us say, I have a light-emitting material that emits with an energy of 1 electron volt. Now here is a question. How much energy do I need to put into the material to get that light out? More than 1 EV, right? That is just energy conservation. You cannot create energy out of nothing. And excess energy can always be converted to heat. In 2D materials, the process is depicted something like this. A high-energy light excites the material, which then emits a low-energy light. But at room temperature, the picture looks a bit different. Something like this. You see, these atoms are not standing still, they are constantly vibrating. And those vibrations are nothing else but a measure of the material's temperature. They are called phonons, and if we can couple to these phonons, that energy is up for grabbing. In a normal scenario, we usually excite the material with light above the band gap. The excess energy is lost as heat, and then we get light emission. But if we excite the material below the band gap, the missing energy can be supplied by the phonon bath, and what we get is upconverted emission. This upconversion process is usually very difficult to happen because it is difficult to couple these phonons to the light-emitting particles. This is where our 2D material comes into play. They are especially well suited for this because the light-carrying particles are confined within an atomically thin plane. This quantum confinement allows them to couple very efficiently to phonons because basically, they have nowhere else to go. And because this process depends on the phonon population, the signal becomes stronger with higher temperature, resulting in higher vibrations, or a higher number of phonons. Which means, if we heat up the material, this signal starts to get stronger. That is why we see an exponential dependence on temperature of this UPL process. And the sensitivity of a material depends on the slope of this graph. With exponential dependence, we get higher slope, and hence higher sensitivity. So to conclude, temperature directly controls the strength of the upconverted light, turning this atomically thin material into an extremely sensitive thermometer.